Thank you everybody for joining us today here on this WebEx. My name is Bob Ranella, Product Manager, like Chris said, over in the Buffalo Grove office for our 3D scanning solutions. I appreciate you guys joining us today for this very informative webinar. Today we'll be discussing portable 3D scanning options and how they are making inspection easier across various industries by answering some of the following questions. We'll cover today what is a 3D scanner and how does it operate. We'll talk about what does a typical inspection workflow look like with a 3D scanner. We'll discuss what are some various inspection applications currently using 3D scanners. Then we'll talk about, we'll see a short video on how a 3D scanner has improved one particular company. And then we'll follow up this information with a live 3D scan and inspection. So, without further ado, to better understand the future, it is always a good idea to take a look at the past. So many may not know that 3D scanning technology has been around since the 60s. The first scanner composed of lights, cameras, and a projector and only performed simple sketches. And the technology didn't quite resemble what we see in science fiction movies. Nevertheless, it did mark the first digitization of a physical part. Fast forwarding 30 years later, we see applications of 3D scanning popping up in the medical field for a full body rendering. And by the turn of the century, 3D scanning made its way into industrial applications. So now in 2018, we can actually do a simple Google search and see that 3D scanning has arrived and it has become a standard tool in metrology applications. So there are many different types of 3D scanners that actually exist on the market today, and the best way to classify them for your information would be to say contact or non-contact scanners. Although when it comes to non-contact scanners, we can break it down a little bit further into two separate categories, passive and active. So for contact 3D scanning, contact 3D scanners, you may have seen some on the market currently in the form of a CMM. And basically they explore the physical object via a probing tip and must be in contact with an object surface in order to collect a 3D point. In order to use this device for inspection, multiple points are needed to create a single measurement. These are considered to be very accurate systems, but the workflow is a little bit more in depth. Moving on to non-contact passive 3D scanners. These types of scanners actually don't emit any kind of light source. They rely on detecting reflected ambient light. Most of these typical types of scanners are usually in the visible light range, but there are a few that actually detect infrared. In most cases, passive methods are generally inexpensive because they don't really require too much equipment besides a digital camera and some sort of advanced software. These are considered, though, to be more on the less accurate system side, and you can find these pretty readily available in the consumer market. Now last, we have non-contact active scanning. In order to probe an object or an environment, active scanning emits some sort of light source, whether it be X-ray, ultrasound, laser, white light, and they actually detect the reflection and frequency of the emitted light on the object and provide it back to a specific optical system. It provides a more cleaner and accurate data because it can control the signal, and they are great for metrology applications. They're considered metrology grade, and they're the ones that are most commonly found when doing inspection applications. Now, knowing a little bit about 3D scanning that exists currently on the market, not every scanner fits every application. This tends to be a gray area for most. So I find it kind of easy if you break it down into 4 specific categories. So the first category we can actually say is accuracy. And when you speak to the volume of accuracy, you have to ask yourself, what is the tolerance requirements of my part? The second thing we would actually look into is resolution. What is the smallest detail on my part? Do I have something that fits in the palm of my hand? Or is it a large casting with very large features? Repeatability. So how many users will be inspecting with this equipment? do you need to have operators up and running 3 shifts during a 24-hour period, and you need reliable resorts that are independent of the user? Or are you you're okay with training one specific person on this specific scanner to acquire certain measurements? One other application or aspect would be environment. Are you working inside a quality controlled lab, or is it an ISO certified lab where we have humidity and temperature and pressure controlled throughout the entire room? Or are you working on the production floor, or maybe even out on a plant floor or in a foundry? Your piece of equipment actually has to fit your needs, and that's why they make a variety of different scanners on the market. Now, Creaform is one specific company that we've seen out on the market and that we actually represent their equipment. They provide a variety of solutions for 3D scanners and inspection, everything from handheld devices to portable scanners to contact and non-contact, and even fully automated QC solutions. They've been developing 3D scanners for over 16 years, and their mission statement is to develop and manufacture cutting-edge technology that fits all industry applications and overall improves productivity. The scanner you see in front of you is a range from specific applications to a wide range of applications with one scanner. Say from a Go Scan aspect, we can have just simple color and reverse engineering applications, to a Handy Scan where we have a wide range of metrology applications and size of parts, all the way up to something like a MetroScan system, or if we have very large castings or very large parts that we need to inspect. So let's talk about specifically active 3D scanning today on this webinar. And let's dive a little bit deeper into how active 3D scanning actually works. So the process of 3D scanning actually starts with applying positioning targets on our part. And by doing so, it gives the part its own alignment. It sets that 000 point aligned to our part. Next, after we go ahead and push the trigger, the scanner itself sees these targets and identifies that alignment. And this prevents any measurement drift from non-ideal environments, vibrations, or issues caused by the operator. If he was to move the part by accident or bump it, the scanner would be able to recognize that the part has been moved because it has its own local alignment. Then the laser crosshairs scan the surface of the part. Finally, it digitizes the surface in real time on screen. Now, we take a little closer look at what is actually going on. The scanner is working in conjunction with the software to create 3D points in a virtual environment that represent the physical surface of the part. Now, when we talk about accuracy, that one category we discussed earlier, we actually are trying to hit a point on the nominal surface. The physical surface of the part, if we were to look at the CAD model or design it in SolidWorks or look at a drawing, is called the nominal, which I already mentioned. And we represent that with a straight line. And ideally, that's kind of how we set up those measurements, from nominal surface to nominal surface. So when scanning or acquiring measurements, we want a point to be exactly on that line. But not every system that exists in this world is perfect. In fact, there aren't any systems that can perfectly match every single time a point on a nominal surface. So when we talk about accuracy of equipment, we discuss a plus or minus tolerance of the actual equipment we call accuracy, and it builds an accuracy window around our nominal surface. And when it acquires those points will float around that nominal surface in a window, creating within a tolerance of your part. Now, that's just accuracy to point on a surface. When we apply this theory to the real-world applications, we need to consider that we're not just interested in a point on the surface of a part, we're actually after measurements from one point to another or one nominal to the next. As you can see, the overall perfect length, if we were to look at our drawing, is 15 inches exact. And ideally, that's what we should measure with our scanner, right? But because of the 3D error due to the equipment and the environment, we could have a range of measurements from point to point, falling in that volumetric accuracy. So when you consider a 3D scanning object for metrology, you really have to take into account the volumetric accuracy of your part. Now let's talk about different common outputs of 3D scanners, output file types. So two of the more common output file types for scanners are point clouds and STLs, which is short for stereolithography. You might be familiar with this file type from 3D printing. It has been a file type that has been around for quite a while. A point cloud is composed of thousands of Cartesian points in a dense volume that kind of outlines the shape of our object. And an STL is composed of many connected small triangles with a normal vector that forms the outer surface of an object. Now, the pros to having an STL versus a point cloud is it makes it easier to do mathematical extrapolations for your measurements. The cons of the STL, though, is the file size is a lot larger than a point cloud. Now let's talk a little bit about the inspection workflow and what it would look like with a 3D scanner. So there are very many different types of inspection workflows with a 3D scanner. And then there's actually many different types of inspection software on the market. Again, I'm going to use Creaform as an example. They developed a software called VxInspect. And VxInspect, inside that software, they have simplified the process down to 6 main workflows that covers pretty much 90% of what all industries need. So we can create an inspection workflow with just numerical data, similar to what a lot of people do with CMMs, where we actually input a nominal measurement, and then we go ahead and verify it on our part. Or we can compose an inspection report with a scan compared to another scan. In a sense, we take a scan of a gold standard and we line it up with our new part and see if they fall in and out of each other or how far out they deviate in our manufacturing process. Others like to verify things in 2D. So we have the ability to create cross-sections inside VxInspect on our part, our digital part, and look at measurements or entities in 2D, such as a circle. We can verify a diameter in 2D of a circle. You can compare point to point using a point cloud, and that's just your simple measure from this point to that point. 3D curves, if you have a lot of organic geometry, it's very hard to verify, so it has options to select 3D curves and see how that curve deviates maybe from a specific value. And then what I like to use mostly is the workflow with the CAD. And this is my preferred method, and that's exactly what I'll demonstrate with you guys live today. So let's go ahead and dive a little deeper into what that workflow looks like. So working with the CAD, in our workflow with the 3D scanner, we start out by calibrating the scanner. Okay, a true metrology measurement system should have its own calibration artifact, and that way you can adhere to those accuracies specified for that system. It's something that you should perform just about every time you're going to go ahead and inspect, and it will actually take into account any error built up from use or the environment, and it will recalibrate your measurement equipment to fall right back into that accuracy. So that's no different when this piece of application, this piece of hardware, we're going to go ahead and scan up our metrology artifact first and make sure it's calibrated. Next, very simple, all we do is scan our part. After we've placed our positioning targets on it, we go ahead and hit the Go button, and we start acquiring the surface of our part. Once we have our digitized model on our computer, we have to go in and take a quick editing step here and delete out any unwanted data. such as a table or a hand or anything else that might be in the area that you acquired. Because really, you don't need all that extra data, you don't need all that extra processing time, and we want to just isolate our part and inspect that only. Next, we import our CAD model, and we use that as a nominal measurement. You can think of this as like an interactive drawing of your part. You already have all your nominal measurements built into your CAD. All you need to do is select the features you want to compare this to and tell the software what tolerance to compare it to. And in this step, we select the features you wish to inspect and have the option to set the tolerance, the GD&T, or color map, which is a great way of verifying a visual effect of whether it's in or out of tolerance. Finally, I like to call this automation step a bonus step. After you've created your first inspection report with all your critical features and tolerances, you can now save that template and apply it to another scan. This way, once you have completed the scan step for the next part, the software will automatically fill in the rest and produce a final report. This is a very powerful tool when you have to inspect batch parts. This tool allows the user to go from weeks turnaround to mere hours. So now that we covered a little bit about the workflow with our CAD model and inspection equipment, let's cover a few applications that we've seen 3D scanners be used in when it comes to quality control and inspection. So when it comes to part investigation, not all inspection is performed in the QC lab. In the tool and design industry is where that theoretical meets the practical, or that rubber meets the road. When we design tools from our ideal CAD model, certain issues occur that are unforeseeable, such as shrinkage, springback, warpage, or other unexplainable physical phenomena. The real question at that point is, how do we adjust and design to fix these issues? This is where 3D scanning becomes vital. Being able to measure the warpage of a part from the tooling and adjust the draft, the thickness, or even our temperatures of our flow to fix the issue with the scanner becomes invaluable, an invaluable tool. So we talked a little bit about quality control. Whether it be pre-production, in production, or post-production, 3D scanning has shown its biggest benefits in the quality control world. Doing your first article inspection reports. Here we have the ability to develop a full PPAP inspection report in the short time it would take to scan the part, as we discussed in our automation step. And again, we accomplished that by comparing it to our CAD for our nominal. This picture actually depicts a color map, or a topographical color map, that represents kind of deviating in or out. So if it's green, it's within our tolerance zone. If it's blue, it's cutting into our part. Or if it's red, we consider that plus material on our part, or out of tolerance. Other applications on the production line is where every second counts. Being able to save downtime and fix issues effectively translates to dollars. Some of the more common issues 3D scanning excels at solving are adjusting jigs and fixtures. To prevent some production drift, we could also do virtual assembly of two parts from separate lines. So if you have two parts of a door being made on two separate lines, and you want to make sure that they're going to line up down the line, down at the end of the line when they're welded together, we could actually scan them during the building process and snap them together virtually. That way, if we have to stop it mid-line, we only lose a few minutes or a few parts versus everything backed up down the line. Now let's take a look at a specific customer application. So you may have heard of a company called Koenigsegg. It's a high advanced sports car manufacturer. The Koenigsegg story is one of humble beginnings. They dedicated their vision and unyielding commitment to automotive perfection. It's kind of a Swedish supercar manufacturer that was founded in 1994 by Christian von Koenigsegg. So let's go ahead and see if you guys can hear this video and see this on the screen. We'll see their customer application.
tried to push the boundaries, but also focus on production engineering, making that full production vehicle. Having ultra-low volume in the production business is a big challenge. We used metrology to quickly identify problems and solve them in the best manner. We really wanted something that would be more flexible and fit in with the way that we work rather than the other way around. Creaform fitted for the purposes.
The Creaform systems, the HandyScan and the HandyPro, has really enabled us to get quick feedback on the quality of the production line between the cars, and also for us to set up our jigs and fixtures and procedures much quicker and shorten the discussion time between what's right or wrong or what affects one another. That has really made a big impact for our efficiency, our tolerances, and in the end, quality and customer satisfaction. For our coming cars, we're already planning to implement the HandyScan, especially in the design process, where we start with hand modeling roughly and going back into the computer and refining it, taking it out via CNC machining, and then modifying it by hand and going backwards and forwards like that. That's already in the pipeline, but also to more and more in the production process, quality check the product and check that everything is aligned even before we might find it.
Good for carbon fiber. Just use on your large surfaces and that's very good to tell because they're not protecting enough. But now with the Creaform equipment, we can scan dark surfaces, or we can scan carbon fiber, so our daily basis material. I would definitely recommend the Creaform equipment. It's easy to use. It's very powerful for engineers because of the accuracy and the speed of use.
I can even see similarities between our product and what we are doing and what Creaform is offering to its customers. We've seen great progress with the Creaform systems over the years. We've been using them, and we can also see we're using carbon fiber to make the product lighter and more user-friendly and have better performance, basically. And that's exactly the same philosophy we're using in our cars, to apply the right material, the most applicable material for the right task. So I think it's a product that goes well hand in hand with what we do.
We try to push the boundaries at all times in our development and the design of our cars. As we say, perfection is a moving target. It's a very difficult challenge to stay on top and stay ahead of the competition. And when we choose partners like Creaform, we're looking for the same aspirations from that company. We definitely feel that Creaform, they're leading the way in metrology, like we're leading the way in technology.
Okay, so that is an example of how Koenigsegg has improved their overall process in their company utilizing 3D scanners. Now, I know we got a kind of a tight bandwidth right now, so that video may have been a little bit choppy for most of you. We'll go ahead and send out a link for you guys if you would like to watch it later, or when you, if you're watching it on the recorded session and it's not coming through as well. So, now that we've seen a few 3D scanning applications, operations, and implementation, let's go ahead and apply some of this knowledge that we've gone ahead and learned to a live application. So what you see on the screen is VX Elements here. This is the software provided by Creaform. And I'm going to go ahead and pop up my webcam here. And on the table, I have my calibration artifact. What we'll do is we'll actually go in and start our workflow. Remember, our typical workflow sequence started with calibrating the scanner. So we'll go ahead and move this down a little bit. We've got our calibration artifact, and we'll go ahead and select scanner calibration. Now, the scanner calibration is pretty easy. It's just a matter of pointing it at the artifact, going through each step, and you can see the green bars on the side, top, left and right side and top, indicate my left, right, front tilt of the actual scanner relative to the plate. All I have to do is line up the center circle, match the tilt, and you can see it actually fly through the status bar on the bottom. And here we'll do a little bit of rotating. And we'll make sure we meet all the requirements. Last one, I believe. There we go. And just like that, a very quick process when it comes to calibrating. The scanner's calibration is optimal. The software actually compares it to its original factory specs. And you can export out this calibration journal if you actually need to meet some ASME or ISO standards. So if you are required to do this for metrology applications, it'll show you the operator, the time of day, whether it passed or failed as well. So we'll go ahead and put our artifact away, and we'll get to scanning our actual parts. So today with me, I have this plastic injection molded part. And I've placed it on this turning table specifically for this webinar. It makes it a little bit easier for me to operate in front of the camera. But it's very simple. All we have to do is press our spacebar or activate our scanner. Our positioning targets I've gone ahead and placed on the part itself and on the turntable for a little bit extra help. I'm going to point my scanner at the part, and we're going to go ahead and pull that trigger. Move this up a little bit. So you'll notice there's a distance bar. We see it as color. Blue is too far away from our part. Red is too close. Kind of like, you know, painting. What we see is what we get. And on the scanner itself, we can actually see that color bar right back here on the back of the actual scanner head. So the operator has use or a visualization too when they're actually scanning. I also have a couple of menu options here. For when I'm actually scanning, I can go ahead and zoom in on screen to make sure I'm capturing all the features I want. I want to focus on a specific area. Go ahead and make sure we get everything around the sides. And you can see how quickly it's actually building our parts. When it comes to accuracy, it picks up the, this particular scanner picks up the positioning points or the 3D points of the surface within microseconds, and it optimizes it. So if I was to hold the scanner on one specific area, it's not going to constantly collect that area, so I don't have large files. All right. We'll go ahead and pause the scanner itself. We'll take a look at our image, rotate it, see if there's anything we missed. It looks like I missed some of this edge and a little bit in this area. We'll rotate it on the screen, and we'll go back over here, make sure we pick that up. Very user-friendly, very interactive workflow. All right. So let's go ahead and move on to our next step in our typical sequence, and that is clean the part. You can see on screen, I have some of the table, maybe some of my arm in the corner over here, and that's unwanted data. Now I can inspect with this, I can continue forward if I want to, and it won't really affect my measurements, but I'd prefer to have my file size smaller. So I'm going to quickly jump into my edit option, and I'm going to say everything that is not connected to my part, or in blue, or actually we'll flip the selection, so everything that is not my part, we'll go ahead and delete. That way, the only thing left is my part. We'll now jump out of that edit option, and we'll let the software complete the scan processing. So we'll go hide those positioning targets. Again, I needed to place them on the part in order to give it its own alignment while I was moving it. I wouldn't have been able to rotate it on the table if I didn't have those positioning targets. But because I put the positioning targets on there, I didn't have to worry about inaccurate measurements caused by moving or vibration. And the software knows the size of the targets, so it actually sets it up as a different layer. Now that we have our scan, there's a couple spots that are missing. I can either go back in and scan those up. I missed a little bit part of this cone. Or if I know I have all my critical features, I can go ahead and move forward. And for the sake of this, we're going to go ahead and move forward. So the next thing, we're going to go ahead and import our CAD model. And again, we treat our CAD model as our nominal measurements. We'll give it a second to upload that. So here we have our CAD model, and we have our scan inside our software. We'll go ahead and jump into our inspection module. Now, the first step I have it prompt me with is actually a alignment option. And this helps with saving my computer some calculating time. I'm going to pick 3 points on both my CAD model and on my scan that are pretty similar. It doesn't have to be exact. You'll notice over on the left-hand square that it's kind of aligned my scan and my CAD, but not perfectly. Once I hit accept, it'll go through and it'll match it up, do kind of a more refined alignment. But by locking those 3 points, it saved my computer a lot of calculating time of trying to find two objects in three-dimensional space. And here we are with our color map right off the bat. We'll actually tighten up this tolerance a little bit more. We'll just set it to, we'll set it to 0.03. So right off the bat, this is a best fit alignment. I can see that there is some parts deviating off of a best fit. Again, plus or minus 30 thou is the green. Red is actually extruding out from our part. Blue is cutting into our part. So with a plastic injection molded part, just off of a best fit alignment, this tells me a couple things. One, the ejector pins were on the back side somewhere in the center, and two, it probably ended up cooling while it was still in a soft state, deforming the center and sagging on the outsides. So if I want to tell my manufacturers, this is what I found initially, we can go ahead and add a snapshot right off the bat here up at the top to show up in our report with that color map. And if we want, we can add a couple of items onto that snapshot as well. Go back into snapshot mode here. Just a couple of bullet points of where it's actually deviating out with some numerical value, because everybody loves numerical value. Now from here, setting up the inspection, is a matter of going through your critical features. So I'm actually going to change my alignment. My drawing specifies that I have a datum alignment, meaning this is going to be my datum A, this top feature. And notice how I'm picking on the CAD itself graphically. I select this top surface. The software recognizes that it is a flat surface. And I can go into my selection items and say, let's label this datum A, and compare this to our scan. Now, it's already pulled up a flatness callout. We can go in here and adjust this as well. And that will now show up in my report with the flatness callout of that top surface. We'll go ahead and select our datum B for alignment, and we'll select the center axis of this column. And what I'm going to do here is I'm going to select all my datums and then realign this scan to those datums so my measurements from my drawings will fit those datums. Now we've got our datums. I'm going to go ahead and add an alignment, and we'll say datum A is my primary, datum B is my secondary, and datum C is my tertiary. And that is per my drawing. Now, if we do a color map, maybe my datums are made from manufacturing. These are things that we measured when we built the tool. But when I add my color map, you can see we got a significant difference. And maybe this will translate back to the manufacturers, the guys designing the tooling, and they'll see that maybe there was something that wasn't cut quite plainer off of this. We'll go ahead and add that color map in and take another snapshot. We'll add our numerical data in here. Into our report, and we'll move forward and start inspecting some critical features. So the first thing I'm going to go ahead and create is a plane on this back side. Then we'll create a plane on the front side. Oops, let me delete that. I selected probe. I have my probe turned on. Go back in, say mesh. Select this back face, and it automatically identifies it on the scan by picking on my CAD as my nominals. I don't have to worry about user error, measuring the wrong point, measuring from the wrong point, or measuring the wrong feature entirely. So we'll actually measure between those planes to get an overall distance. And we only want the X reported in our report. So over here on the left, you'll see my dimensions. This is where we'll actually set up our tolerance zones. We have a plus and minus tolerance. I can go ahead here over on the left and say we'll change this to 0.0, 5 thou, minus 5 thou. And we'll have that show up on our report, the overall measurement. So what's going to show up on my report is my nominal, which is my CAD value. I didn't have to type that in. That was pulled off the CAD. The measured value, which was of this specific part, and what's the deviation. The tolerance will also show up on the report. It just doesn't show up in this quick view list. As we can see, it's got a check mark, which means it's within tolerance. We'll go ahead and grab a few more things. We'll grab this cone over in the corner. And we'll have, let's just go with X, Y, Z information. Let's just put all the information in our report. We'll even go further. Down at the bottom here, we have GD and T information. So we'll say, what is the true position within, I don't know, 30 thou to datum A, B, and we'll even say C. And we'll put that on our report, which is going to fall out of tolerance. So we've got all those points, X1, Z1, X2, Y2, Z2, our GD and T, all that's going to show up in our report. We can even have a call out with a snapshot if we want of these specific items to show up in our report as well. So we'll go ahead and take a snapshot of that so our person who's reading the report has a better workflow or idea of what we're actually pointing at if they don't have the drawing in front of them. So we'll go a little bit further and we'll grab a surface. We'll say, what is this surface deviation from our actual CAD model? And we'll add a profile tolerance. To A and B. All right. And we can see graphically the color map doesn't match. So with my 5 thou tolerance, unilaterally, we're a little bit out. Next thing we can do is we can add a little bit of 2D dimensions. We'll use, since these are drafted cones here in the center, we'll throw a plane here, or we'll use plane datum A, and we'll drop it down to a certain distance. Actually, you know what? I apologize. We'll create a new datum to get this cone, this inner cone. So I've just selected that top plane graphically, and I'll say, grab a 2-dimensional cross-section of that. Now when we look at it in 2D, we've got something similar to what we'd see on our drawings. And now I have a whole new world of inspecting in 2D. I can say, grab this, compare this inner circle, or this outer circle, to the actual datum, or the actual physical model. We'll do the inner circle. And we can set our overall color tolerance map if we want to, depending on our constriction, what's acceptable and what's not acceptable, and we'll have that show up in our report as well. So we can do 2D, GD, and T if we need to. We can do 2D verification if we need to as well. And we can add that snapshot into a report if we wanted to as well. And I'll go ahead and do that. Let's say cross-section, circle, snapshot. All right. So we've got a few pieces of information. This is kind of the workflow you'll go through when using a 3D scanner. All these items that I've created down here in my inspection program are my critical dimensions and my features that I want to show up in my report. Additionally, it is a saved template. So we're going to go ahead and export out this particular report and take a look at it. And then we're going to scan up another part, and we're going to go ahead and see how it compares to our report for that extra bonus automated step. So we'll give it in a second to export. So we can put our project customer name if we want to on top, time, operator's name. We've got a snapshot of our color map. We've got our datum A, B, and C, so we know what datums we've used. We've got our GD and T flatness call out. Our distance, remember that was a plus or minus 5 thou tolerance. There's our nominal, there's our measured. There's our deviation. This didn't bubble in red because it was within tolerance, but when I did my true position, which you can see the ballooned item over here that it automatically put in with the tolerance. We can see it was out of tolerance and it ballooned it in red on our report. So it'll automatically stand out to us that there's an issue. And then it'll show me my primary, secondary, and tertiary deviation from nominal to measured values. And all these calculations are inside the software. All I had to do was pick them graphically off the CAD model. Here's our 2D verification as well. We'll zoom in a little bit with our circle. All right, so what I'm going to do, we'll pop our webcam back up here. We'll go ahead and start, we'll use this program and we'll inspect another part. So all I'm going to do is go up here once I've had my program created and hit Add Part. It's going to clear my entire inspection program. It's going to save the initial one over here in my tree. Now I'm on Part 2. Once I hit Measure All, I begin my process. We'll go ahead and put this part on here. And we'll begin our scan process again. Same as before, as long as we acquire the surfaces, what we see on our screen is what we get. And I'm going to go ahead and zoom in here. We can see a little bit better of what we're capturing. Make sure I get all these edges. I didn't get too many of the critical features for time's sake. So I'm just going to focus on just gathering the items that I did acquire. You can see over on the right it has highlighted in orange. Another added bonus. The one thing I didn't mention before, this particular scanner does have a single laser mode, so I can get into that little crack that I missed before. Kind of like a fine paintbrush. Now, I didn't need to scan this entire part if I only have those few critical features. I could have just focused on those. But because I scanned this entire part, if I ever want to go back and gather more critical features off this one scan, I have it saved. So I don't have to go back to my part and actually scan it. I've got it saved in a digital file, which helps alleviate some of the bottlenecks of inspecting, running back to the part, gathering information, running back to the lab, and figuring it out in a report. Again, we'll get rid of some unwanted data that we don't want. We'll let it process. We'll pick our 3 points. We'll accept it, and notice the inspection program has question marks on it. It is now going through and it's updating each one of those critical features with the new scan, and just like that, I'm completed with my second part. So already I've cut my time of inspecting 2 parts less than half. And as I continue doing part 3, part 4, so forth and so on, my time is saved exponentially using a 3D scanner. Now when we export out this report, give it a second to pop open Excel here. So now when we export out our reports, we will see that we will have 2 reports in our Excel spreadsheet. Right down here on the tab, I have Part 1 and I have Part 2. And as many parts as I have, I'll have down here on the tab. And the benefit of doing this is now I can grab the deviation or measured value of Part 1 and Part 2 in Excel, F77, and I can write a macros to get my CP, CPK values, or maybe run a gauge R&R on my process to see if it is reliable manufacturing process. And that's how we use a 3D scanner to improve inspection and quality control applications, and how we make inspection a little bit easier. So at this point, we are actually at the end of our WebEx. We have somewhere around 7 minutes left. I'm going to go ahead and see if we can pop open that chat box and see if you guys can go ahead and send me over any questions you might have to answer. Again, if I can't get to all your questions, we'll see if we can respond via email back to you. So, your chat is over in the corner of your WebEx window. If you have any questions, please type them in there.
Hey, Bob, this is Chris.
Yes.
I kept track of a couple of questions that came up throughout the presentation.
Okay, perfect.
One question was, do all the scanners require placing those targets on the part?
That is a very good question, Chris. Now, for metrology applications, most of the scanners need positioning targets in order to hold the accuracy. Creaform uses a MetraScan system for larger parts where you don't necessarily need to place positioning targets on your part, but then again, you would have to lock your part down on a granite table so you're not susceptible to vibrations or in some sort of jigger fixture. So it's entirely up to you. If that is the route you want to go, you have that ability with the MetraScan. Otherwise, with the HandyScan, I can free and clear, move my part, and still not worry about any error due to inspection. Great question, Chris. What else did you come across?
Do you need to optimize the model prior to editing was another one that came in.
So Eric, are you referring to optimize the CAD model, or are you referring to optimize the scan?
Specifically the scan he just mentioned.
Right. So you don't need to necessarily optimize the scan after you scan up your secondary model. So you can continually scan, and you may be referring to the processing method. After each scan, we do have to let the computer process and rebuild it so it does have optimal measurements. That might be something that you're referring to. All right. What else do you got for me, Chris?
Quick question. What scanner was that you were using?
That was the HandyScan 700. It's actually one of the scanners that we've seen most people use in inspection applications. We'll go ahead and pop this open real quick. You guys can go ahead and see that on screen. So this one is very handheld. It is actually fits in a Pelican case. It's plug and play USB 3. I like this one specifically because it has 7 lasers in that single laser mode. I mean, it's very easy to use, very easy to learn. There are other scanners out there, the MetraScan, which is a 2-part system, and there's the Handy Probe, which is a wireless probing system as well. So this one comes in a 7-laser scanner, which is a 700 model, HandyScan, and it comes in a 300 model, which is a 3-laser scan, but it is less accurate. It still works for metrology applications. Again, you have to ask yourself, what are my accuracies that I'm trying to meet? Good question. What else do we got?
Any recommendations on a workflow for a quick one-off part inspection?
Well, it really depends. I mean, you just saw it here on live on WebEx. I mean, for a one-off workflow, I mean, our entire time on WebEx was about an hour. And in that amount of time, you could do a one-off really quickly. So you could take the workflow that I just demonstrated for you, or you can go a little bit different and just enter numerical values. So you're talking about a 5-minute inspection, Brian. That really depends on how many critical features you need to do in 5 minutes. You saw when I automated the process, quickly re-verifying all those critical dimensions was less than 5 minutes. So if you needed to just quickly grab 1 or 2 measurements, you don't have to do that in the inspection software. You can scan up the parts and manually pull those measurements. Just say, give me the measurement from here to there, or point to point, or plane to surface. You're welcome, Brian. Looks like we're rounding the 2 o'clock mark here at Central Time. I appreciate your time on this inspection. Before you guys actually go ahead and leave, I have one more thing. Okay, so upcoming webinars. We do have model-based definition. What is it? What should it be? That's in July 12th. Catapult session, SolidWorks, July 19th. Stratasys applications, end user parts, which is, I like that one, is July 31st. And Innovia PLM webcast. It's always good to know more about Innovia PLM. You can never know enough information about that on August 7th. So if you guys have an opportunity, please go ahead and sign up for those as well. Thank you guys very much for your time, and I will see you next time.